So, good evening, everyone. I am Avinash Agasti, a PhD scholar in the Department of Electrical Engineering, IIT Madras, and I will be taking these tutorial sessions where we'll kind of discuss on some kind of problems, questions, and numericals or whatever you might like relating to the course content corresponding to the week. Like for today, we'll discuss whatever you have studied in week one and like some questions that I think would cover the most important concepts of the topics you have studied in week one. And since there are very few of us, uh, we can make it as interactive as possible. So if you have some doubts at any point of time while I'm talking, you can just unmute yourself and interrupt me. So yeah, is there anything else you expect from these tutorial sessions? Yeah, don't feel shy. Okay, so then maybe we can start. And as things come along, if you have any issues or queries, you can just unmute yourself and interrupt me at any point of time. Okay. So I hope you all of you have gone through the course lectures of this week, week one. Can one of you summarize what all you have learned in this week? Yash, if you don't mind, can you summarize what you have learned this week? Okay, no response. Okay, so I'll just start with the questions, and if you have any issues, you can. So, for a system P having an input U and an output Y, which of the following properties is or are not necessary for the system to be linear? So, can you guys just type in the chat box what uh, are the two necessary conditions for a system to be linear? Yeah, so I was asking uh, to type up in the chat box you have in the bottom right. What are the two properties necessary for a system to be linear? What is the definition of a linear system? Yes, so Ankita has given the right answer. So linear system. Yeah, are you guys able to see what I'm writing on the screen? You can just type a yes in the, yeah, thank you. So a linear system can be any system which takes in a certain input U and gives out a certain output Y, right? And for a system, for any such general system to be linear, we need two conditions. One is additivity and homogeneity. So this is essentially the principle of superposition. So what that says is, if I give U1 and the system outputs Y1, and when I give U2, the system outputs Y2, then if I give U1 plus U2, the system will output Y1 plus Y2. And if I give alpha U1, then the system will output alpha Y1. So both of these rules can be summarized into one single sentence, which can be written as alpha 1 U1 plus alpha 2 U2 shall give me alpha 1 Y1 plus alpha 2 Y2. Okay, so this is the condition for a system being linear on the inputs and the outputs. So based on that, Which of these four options is the correct answer to this question? So the question is, for a system P having an input U and an output Y, which of the following properties is or are not necessary for the system to be linear? So uh, can you guys type up the answer that you think, the option number? So this definition is clear, right? What a linear system is. So based on that, you can try to figure out which of these options. Okay, let's first figure out one by one. Let's take the option one. Yeah. So we were discussing the first question, which essentially says which of the following properties is not necessary for the system P to be linear given inputs U and Y. So let's start with the option one. U1 gives Y1. The particular system, when you give the input U1, the output received is Y1. Then is this condition necessary for the system to be linear? So I know that given input U1, the output is Y1. So if the system is linear, when I give 1 by alpha U1 and 1 by alpha Y1, should the, like, sorry, if the system is linear, when I give the input 1 by alpha U1, should the output be 1 by alpha Y1? Right, so what is the answer? You can just type a yes or no. Whether if you think this condition is necessary, just type an yes, and if not, just type no. Okay, we've got one yes, and the others, just make a guess. Then maybe if it's wrong, we can think about it. Yes. Any other answers? Okay, so clearly you can see we had one of the properties as this. If I scale the input by some, so here alpha is some positive, is alpha is any real number. So if I scale the system by any alpha, then the output must also be scaled for the system to be linear. So here we are scaling the system, the input, by 1 by alpha. So by the consequence of linearity of the system, the output should also be scaled by 1 by alpha. Okay. Now take this condition. I am saying that for a given output y1, the input required is u1. Then is it necessary that for 1 by alpha into y1, the input required be u1, 1 by alpha into u1? No, okay. Any other answers? Any other guesses? Whatever you might think is right. Yes? Anyone else? Okay. So the thing is, we want scaling any input to have a scaled output, but there is no restriction on the opposite sense. Like if I have a 1 by alpha y1. I need not have 1 by alpha u1. If u1 gave y1, then definitely 1 by alpha u1 will give 1 by alpha y1, but the opposite need not be true. So this might also be true, but it is not necessary for the system being linear. So here we have, this is yes, this is no. Okay, and then now what is this? If u1 gives y1, u2 gives y2, then u1 plus u2 gives y1 plus y2. So what should the answer be here? Is it necessary? Yes, because this is itself one of the primary conditions for the system being linear. So here the answer is yes. And the last one, if 1 by alpha u1 gives 1 by alpha y1 and 1 by beta u2 gives 1 by beta y2, then should the sum of these inputs, 1 by alpha u1 and 1 by beta y u2, give the sum of these outputs? Is it necessary for the system to be linear? Again, a yes. So this is also the principle of additivity and the previous one. So this one is homogeneity. This is not there. And these two are additivity. Okay. So is it clear? We'll move forward. If you have any doubts, you can stop me. Now we have that the impulse response of a linear system is which of these following options. So first, can someone just quickly type up what is the definition of the impulse response of a linear system? Or you can also go ahead and unmute yourself and talk. So we have an answer which says bit 1. Okay. So can someone just define what the impulse response is for a linear system? Yeah, that's it. So essentially the impulse response, so I have a system, let's say P, and I give some input. Some input will warrant some output for the system. So for this input u of t, the output y of t is the response. So what does impulse response mean? So impulse response means if I give input as the impulse signal, that is del of t, then what is the output? Output h of t is the impulse response. Okay. So what is del of t? So this is the time axis, this is the magnitude. So del of t function is just an impulse at time t equal to 0. Okay. So this, let's just rule out this option first. The response when an impulse train is applied to its input. The impulse train, on the other hand, this is del of t, but an impulse train is, as the name suggests, it is a train of impulses. That is, it is something like this. So it is a complete series of impulses spaced equally at some regular time intervals. So, but that does not give us the impulse response of the system. So this option is wrong. Then again, by definition, we just consider the output of time t excited by this impulse. Like for impulse response, we just consider the standard del of t function, and there is no time shift in the impulse. So del of t minus t1 would just be an impulse at time t1, but we don't consider that. So this is also wrong. Now this one, the inverse Laplace transform of its transfer function. So let's try to see why that is the case. Yeah. So let's say we have a linear system x dot equal to ax plus bu. Let's say this is an LTI system. Then, and let's say y is equal to cx plus du. Okay. And we put u of t is equal to del of t. Okay. So we'll have x dot equal to ax plus b del of t. This is so x dot of t is equal to ax of t plus b del of t, and y will take it as h for the impulse input. So we'll have x of t plus t del of t, right? So I want to see whether the inverse Laplace transform of its transfer function is the impulse response. So first let us see what the impulse response in terms of state space dynamical, like that kind of result is. So can someone tell me, for this x dot equal to ax plus b delta t system, what is the solution x of t? Yes, can someone tell me the formula? Okay, I'll write it down. So we have e to the power at x naught plus integral 0 to t e to the power at minus tau b into delta tau d tau. Okay, so this is the solution, right? So that means h of t is just c x of t plus d delta of t. Now I want to see whether this transfer function, like, so if this option is correct, then h of s by u of s should be equal to the Laplace transform of the impulse response. Okay, so we need not even go that far for this thing. Like we directly have that the so the we want to show that the impulse response, that is the h of t, is equal to Laplace inverse of its transfer function. Well, you know that the transfer function is given by y of s, where y is the output, by u of s, where u is the input. And in this case, it's just quite direct, in the sense that u of s is just the Laplace transform of delta. So this is nothing but 1. So clearly this condition holds, because h of t is just Laplace inverse of h of s, which is the output. Okay, is this clear? We need not go about solving the system or anything. We just directly have this for the impulse response. Is it clear? So this is the correct answer. Okay, so we'll move ahead. Now we have this system, LTI system, right, given by some A matrix and B matrix. Find the Frobenius norm of the corresponding discretized A matrix resulting from the continuous time system AB. Your sampling time T is something. So, first tell me, how do we discretize the system? So, I have some x dot equal to ax plus bu, and I want to discretize the system. That is, find a discrete equivalent. I don't want to have any x of t. I just want to have some x of k instead of a continuous time domain. So we have this continuous time LTI system. So we know its solution x of t is equal to e to the power at x naught plus integral 0 to t e to the power a t minus tau b u tau d tau. All right. So if I discretize this x, so I have a continuous system that is not going to become discrete. So I have a continuous system and I'm, let's say, measuring the state or something. Then I'll then discretize that. So I'll define x of k as x of k into some sampling time t, where t can be defined as per any problem. So here xkt is e to the power akt x naught plus 0 to kt e to the power a kt minus. Right, now let's write xk plus 1. This is again xk plus 1 into t. This is xk plus 1 into t. And then we have, this is e to the power a k plus 1 t x naught plus 0 kt e to the power a k plus 1 t minus tau. This is also k plus 1, sorry, d u tau d tau. Now, can you now find a relation between xk plus 1 and xk? Some form of xk plus 1 is equal to some function of xk or any such kind of relation. So for those who have joined just now, what we are trying to do is, we have a continuous time linear LTI system with given A and B matrices. We want to find the norm of some discretized A matrix resulting from the continuous time system. Okay, so we have this continuous time system. I want to discretize that thing with some given sampling time. So how do I do that? So maybe you guys can try writing xk plus 1 in terms of xk, given that we have these expressions. Okay, maybe you guys can try for some time, then we'll discuss on it. Yes, so any luck on this? Okay, I'll write it down. So if you see, xk plus 1 is equal to e to the power at into plus right. So this is just e to the power at into xk plus kt 2k plus 1t e to the power a k plus 1 t minus tau. This is just algebra. You can do it. Theta. Okay. So now this becomes the new A matrix, and this becomes the, so we now have something of yeah. So this is the new relation that we have for the discrete system. Now I want to find out the some norm of the discretized A matrix. So this is the discretized A matrix, let's say A tilde. So for that we'll now use MATLAB. Okay, I'll stop sharing my screen here. Yeah, is my screen visible? The MATLAB screen. It is not visible. Uh, okay, I'll just share once again. Yeah, is it visible now? Okay, I'll go ahead. Yeah, thank you. So we have this A matrix. We had this A matrix in the question. This was the B matrix. Then we can take some random C matrix and some D matrix. Then we can create a system sys from this state space function that we have in MATLAB, which is an inbuilt function. So for this SS function, then you put in the brackets and just plug in A, B, C, D, which are the four corresponding matrices. Then you'll get the C, the system. Wait, just 1 minute. So you can see this is the original system in continuous time. 2302 is the A matrix, 26 is the B matrix, and these are some C and D matrices. Now there is a function C to D, which essentially, as the name suggests, converts a continuous time system to a discrete system with a given sampling time. Right. So the discrete sys is our solution. So this is the discretized A matrix and the discretized B matrix. But now, so MATLAB gave us this really nice answer. Then maybe we can find the norm using another function that they have. So you can search norm and you'll get this one. Yeah, you get a variety of options, and in each norm you can choose. So like here, I can, so I guess discrete is, yeah, this is the discretized matrix. So I can take norm of this answer, find the Frobenius norm, and that's it. We get the Frobenius norm of that matrix. But then I'll stop sharing this and go back to the slides. Yeah, so you can see this. I had that e to the power a into the sampling time is the solution of, like, is the new discretized A matrix. But now, how do I, I want to find out it for AT. It is my new discretized matrix. So we all know that e power a small t is given by Laplace inverse of Si minus a inverse. Okay. So after finding this e power a t small t, like a function of time, I can just plug in time equal to t. Then that will give me the, so based on that I can then find the new discretized A matrix. So let us find out e to the power 80 first. So let us first write Si minus A inverse. So okay, let's take some 2 minutes to try to solve this Si minus A inverse. So everyone please try for some time. If you face any problem anywhere, you can tell me there, but it would be beneficial if everyone tried it for themselves. Okay, so anyone tried? We'll go step by step. So first, let us write Si minus A. It will give me this, right? Then its inverse we can find out by simple formulas that we know since quite a long time in school. So this gives me 1 by s minus 2, 0, 3 by s minus 2 whole square, 1 by s minus 2. Okay, so this is the Si minus A inverse matrix. Okay, is it clear up till this point? Any doubts? So then I want to find out the Laplace inverse of this matrix, right? So we'll do that element wise. The Laplace inverse of s minus 2 is just it for 2t. That of 3 by s minus 2 whole square. What we can do is, well, it is just of the form 1 by s square is what? It is the Laplace transform of t. So s minus 2 means it is a like e to the power 80 shifted thing. So we have e to the power, now we have e to the power, sorry, yeah, so 1 by s minus 2 is just e to the power 2t, and this one 3 by s minus 2 whole square, that we can write as 3t e to the power 2t, and this is again e to the power 2t, 0, 0. So this is the e to the power at matrix. But remember, what did we need for the discrete thing? E to the power capital A capital T, where T is the sampling time. That was the discretized A matrix, right? So in this T, we will just plug in capital T, and the resulting matrix that we'll get 0.002, 0.006 into e to the power 0.002 e to the power 0.00. This is the discretized A matrix. So if you find out the values, actually corresponds to, I've run out of space. Just a minute. Yeah. So this value equals 1.00. I'll check the values again. 1.7, yeah, 1.002, 0.003006, and this is the same thing. So now if you look back again to the MATLAB plot, huh? So the discretized system by MATLAB gave us this solution, right? And we also found out that the discretized A matrix e to the power A capital T is also this exactly the same thing. So that verifies our answer. All right. I'll share my writing pad again. So anyone has any doubts, please free to ask right now. Yeah. So is this clear? This is the solution that we got through MATLAB as well. So for understanding how do we discretize, go through this method. But if you want to use it for any practical purposes, it is always better to take the help of some software. And I hope you guys have got MATLAB access by enrolling to this course. So try to make as much use of it as possible. Okay, so we'll move ahead now. So for an LTI system x dot equal to ax, that is for an autonomous LTI system with given, sorry, this is the A matrix A. What is the matrix exponential? So this is quite direct. It for AT, we want to find out. So can someone write down what is it for AT? We already know the formula. It is Laplace inverse of SI minus A inverse. Okay. The same thing we did in the previous question. We had A matrix, we found out SI minus A inverse, then took its Laplace inverse to get the matrix exponential. Alright, so come on, try for some 2 minutes, let's say, then we'll discuss on this. Please keep trying, guys. Is anyone done, or should I start the solution, or should I wait some more? Okay, I'll just go ahead. Yes, do you have the solution, or should I wait? Is I didn't get what you're saying. Could you just say, should I wait or should I move ahead? Okay, then please tell me the steps. Let's first write down Si minus A. What is this matrix? If you don't mind, can you just unmute yourself and tell the answer? S minus 2 minus 4. Right, right. Then, right. So, what does this give us as elements? 1 by S minus 2, 4 by S square minus 4, 0, 1 by S plus 2. So, how do we find out the Laplace inverse of S minus 2? 1 by S minus 2. What is the Laplace inverse of this? Uh, I think the power of 1 by the Laplace inverse of S 1 by S minus A is e to power at. So here we'll have e to power 2t. And in this case, we'll have e to power minus 2t. Okay. And then for the other option, let's first break it down. Okay. We want to write down it this as 1 by A by some A by S minus 2 plus some B by S plus 2. So then we'll have that A plus B S plus 2 into A minus B equal to 4. So that means B equal to minus A and A minus B equal to 2. So from this, it is clear that A equal to 1 and B equal to minus 1 is a solution. Okay. So this term 4 by S square minus 4 can be written as 1 by S minus 2 minus 1 by S plus 2. So that just gives us Laplace inverse will give us e to the power 2t minus e to the power minus 2t. So we have this, and then e to the power at, which is the Laplace inverse of this matrix Si minus A inverse, is given by e to the power 2t, e to the power minus 2t, 0, and this is e to the power 2t minus e to the power minus 2t. Okay, is this clear? Yeah. Okay, so let's just okay, yeah, we can also check this in MATLAB. I'll share my screen. Yeah, is the MATLAB screen visible? So we had this A matrix, right? 2, 4, 0, minus 2. Yeah, and we can take a function t. Okay, this is a like while solving, what we did was we took the inverse Laplace transform of the Si minus A inverse matrix. But when we are using some software, we can just directly take, like in MATLAB, we can take a symbolic variable t, which essentially introduces it as a variable in the classical sense that we know it. So we have a and t. Then we just want to find out the matrix exponential, which has a function by this expm that denotes the matrix exponential expm. So you can see here, yeah, this is the matrix exponential. Then we just want to find out the matrix exponential of a into t. So if I run this, then yeah, this is the solution that we get. It's bar 2t, it's bar 2t minus it's bar minus 2t, and it's bar minus 2t. This one is 0, right? So is it clear? Yeah. So I'll move back to the writing pad. Hmm. So this is the solution that we get, right? Then, okay, now we have which of the following properties are preserved under an equivalent transformation. So I'll just write what an equivalent transformation is. It is just kind of a change in the coordinate system where P can be some full rank matrix. Okay. So originally we had a state X, and then we had some system X dot equal to AX plus BU, and this is Z dot, this is Y equal to CX plus DU. This was the original system. Okay. Then we make a transformation given by X equal to PZ. Now if I substitute that, X dot becomes P Z dot, and that becomes equal to APZ plus BU. So I have Z dot equal to P inverse APZ plus BU, and Y becomes the output. Y will stay the output itself. Here we'll have CPZ plus DU. Okay. So under such a transformation, which is termed as an equivalent transformation, which of the following properties will remain preserved? Like if I go from this system, consider this as system one, and this as system two, then which of these properties won't change? Like let's take eigenvalues for example. If I have some eigenvalues for system one, are those are those same when I try to find out the eigenvalues for system 2? That is the question. So, does anyone have an answer, or do you want to take a guess? What do you think the answer should be? Maybe you guys can type it up in your chat box. Yeah, which are the ones you think? Okay, just try to make a guess about which are the ones you think should be preserved under such a transformation. Okay, there's a guess. Eigenvector. Any others? Eigenvalue. Okay. Eigenvalue got another vote. Anything else? Transfer function and roots of characteristic equation. Anyone bets on those? Okay, let's see how this happens. Right. So, how do we find the eigenvalues of a system X dot, like the system in system one? We know that the eigenvalues are given by this equation, where if we solve for lambda, we'll get the eigenvalues, right? So, let's say these are some of the solutions. Let's say lambda 1 till lambda n are the solutions of this equation. Then Then we can just take for the new system, all right. We can take lambda I minus P inverse AP is equal to 0. I want to solve this one to find out whether eigenvalues have the are same or not. Okay, so I can write this as determinant lambda P inverse P minus P inverse AP. Now this is equal to determinant of P inverse into lambda I minus A into P, right? You can verify this. Then further equal to that is further equal to determinant, because the when we multiply two matrices, the determinant of the multiplication of two matrices is the multiplication of the determinant of those two. So this we can write as det P inverse det lambda I minus A det P equal to 0. Now see, these three terms, they are just scalar values, and we know that determinant of P inverse is 1 by determinant of P. So these two will essentially get cancelled. So here what do we get? The determinant of lambda I minus P inverse AP equal to determinant of lambda I minus A. So obviously this equation, since the LHS are the same, that means when I try to solve for lambda in these two equations, I'll get the same set of solutions. So lambda will remain same. Okay, so this is one answer. Now let's keep eigenvector at bay for now and think about transfer functions. Okay, just a minute. Let's take this one now. Uh, so is this part clear? So we have one answer which tells us that the eigenvalues will remain the constant. Then I want to see whether the transfer function will remain constant or not. Alright. So first, okay, someone just type up quickly what the transfer function of a system like this is. Y of s by u of s. What do we have? So if you think about this, then let's just take Laplace transform of all of those. And for transfer function, remember that we take all initial conditions as 0. So for this system, we'll have s of x of s equal to a x of s plus b u of s. Now this implies, okay, just x of s is equal to si minus, let's just club these terms together. So we'll have minus equal to, so this is si minus a x of s equal to b u of s. So x of s is si minus a inverse b U of S. So now Y of S is C x of S plus D U of S. This means this is C Si minus A inverse B plus D into U of S. So this term is the transfer function. Alright. So we'll see. So let's write so this is the transfer function for system 1, right? Tf1 is equal to C Si minus A inverse B plus D. And then Tf2 I want to find out. We'll just, instead of A, B, C, D, we have some separate matrices, that's all. P inverse AP, B, C, P. Okay, here we'll have a P inverse P, D. Okay, so we have CP Si minus P inverse AP inverse P inverse B plus D. So if we see, this is CP into, again we can write this as P inverse Si minus A P whole inverse P inverse B plus D. Now remember that if I have AB and I'm trying to find the inverse, then this is equal to B inverse into A inverse. So this one is CP into, so here we have A, B, C inverse. Okay, so it will be C inverse, B inverse, A inverse. So first inverse will be of this, then of this, then of this. That will be the order. So CP, then we have the inverse of this, that is P inverse. Then we have the inverse of this, that is Si minus A inverse. Then we have the inverse of this, that is P into P inverse B plus D. Now this boils down very simply back to, but what is this? So this is nothing but this transfer function itself. So we also see that the transfer function is preserved under such an equivalent transformation. And the characteristic equations are nothing but the denominator of the transfer function in some sense. But for a MIMO system, this equation essentially, lambda I minus A that is equal to 0 is the characteristic equation. So clearly the roots of the characteristic equation will be equal to the eigenvalues. So this is also preserved. Now coming to eigenvectors, will it be preserved? So when we want to prove something, we have to prove it generically like we have done for eigenvalues and transfer function. But if something is wrong, then it is enough to just give an counter example. Okay. So if I give you an example where by a equivalent transformation, the eigenvectors are not preserved, then we need not prove anything anymore. Okay. So I'll share my MATLAB screen to give you such a counter example. Right. We have, okay. Let's take a matrix P, which is 2, 1, 1, 3, and a matrix A. Just a minute, I'll just clear everything. Then let's take this. So we have a matrix P, which is a full rank matrix. So that denotes my equivalent transformation X equal to PZ. Then I have some system A, B, C, D. Then IA provides the provides a eigen value matrix and an eigenvector matrix. So the first output of this function IA will give me a matrix of eigenvectors, and the second thing will give me a diagonal matrix whose diagonal entries will be the eigenvalues. Alright. So if you see of the old system, that is without the transformation, that is x dot equal to ax plus bu, the general system, we have this is the eigenvector matrix. Okay, 0, 1 is one eigenvector, 1, 0 is another eigenvector. Now the corresponding eigenvalues are 3 and 4. Okay, because you see this is just kind of a scaling on the identity matrix. So the eigenvalues are also of that form, eigenvectors, and these are the corresponding eigenvalues. But now when I transform the system, that is take the eigenvalues and vectors of P inverse AP, then this is the eigenvector matrix, while this is the eigenvalue matrix. Now see that the eigenvalues in like the eigenvalues in themselves have not changed. This order has changed, but that does not matter. The solutions of the determinant lambda I minus a equal to 0, that thing is same. So 4, 3 here, 4, 3 here. But the eigenvectors, they are not the same anymore. Right, here we just had 0, 1 and 1, 0. But here we have something different, totally different. Right, and then we can just verify. So we have seen that the eigen values match. So this is a verification of our proof. And similarly, we can verify for the transfer function. All right. So for the old system, we can use a function ss to tf, which just takes a state space representation to its transfer function representation. So given ABCD matrices, the transfer function is given by 2s minus 6. So this is basically the numerator and this is the denominator. S square minus 7s plus 12. Okay. While the new one, it is also 0 to minus 6, 1 minus 7, 12. So you can see that the transfer function also is preserved using such an equivalent transformation. Okay, is it clear? Anyone has any doubts? No doubts? So we'll move ahead to the next question. Yeah. So this part is clear. Then we move ahead. Given the matrix exponential, find the corresponding state matrix. So we know that e to the power at is Laplace inverse Si minus A inverse. So the other times what we had was we knew the A matrix and we wanted to find out the e to the power at matrix. But here it is the other way around. We have this exponential and we want to find out the original A matrix. So let's take Laplace transform on both sides. That gives me at is equal to Si minus A inverse. Okay, so just a minute. Yeah, so let's take the, okay, so maybe you guys want to try this out. First, find out the Laplace transform of e to the power at. Maybe we can try this for 2 minutes, then we'll discuss. Just find out the element-wise Laplace transform of this given matrix exponential. Anyone has a solution? Drop in a text in the chat box when you get the solution. We'll start after that. Okay, should we try? So if you find out, does anyone have the answer yet? Mm, okay, so we'll try this. Take the in element wise Laplace transform. We have 2 by s minus 3 minus. Okay, okay. I think there has been a mistake. This is it for 3t, not 3 into t. Okay, sorry for that. Yeah. So this is the Laplace transform. Then we want to find out Si minus. So this is now equal to Si minus A inverse. Now we'll take its inverse to find out Si minus A. Okay. So, or maybe a better way to put this would be we can write this as S minus 3, S minus 1 into, well, 2, S minus 1 minus S minus 3, S minus 3 minus S minus 1, and so on. Okay, we can put this up. Now we see that this is equal to, now we'll get a Si minus. Okay, we have an answer minus 2, 1, minus 4, 5. Okay, I'll have to try that. Just a minute. So we'll have this. Can you just tell me the steps that you've got? This is into S minus 2 plus 3 plus 1. Okay, reverse procedure in the sense. I think this is the matrix that we'll get. Then we can take the inverse of this thing. Okay, I'll just erase this part. So this is equal to this. Then we want to take its inverse. Then we can just find out it is s plus 1 into s minus 2 minus plus 8, and this will be inverted. So we'll have s minus 3, s minus 1. Then this is s minus 2, s plus 1, 2 minus 4. Okay, so this is s square. So if you just do all the calculations, in the end, what you will get is I'll just directly write the answer. Maybe I would have been wrong. Minus 2, minus 1. Okay, this is the A matrix that you'll get. Now, just to verify if we are correct or not, let's try it up in MATLAB. Okay, we clear everything out. Then I have this. This is the matrix that I found out. 5, 4, first column. So let's take this. So I have A is equal to 5, 4 minus 2 minus 1. Then I want to find out the matrix exponential. Alright. So, okay, we do this and then this. So this is the matrix exponential that we get. So which is 2 e to the power 3t minus e to the power t, e to the power t minus e to the power 3t, 2 e to the power 3t minus 2 e to the power t, 2 e to the power t minus e to the power 3t. So this is the original matrix exponential that we were given. Alright, so turns out this is the the given A matrix. So your elements also look the same, but perhaps there was a mistake in some transpose maybe. I don't see that, but yeah, maybe if you try that again, you'll get this solution. Okay, so I'll stop sharing this, go back to my writing pad. Okay, so next we have, okay, this is a simple one. We have an LTI system, A matrix, B matrix, C matrix, all right. And then we want to find out the transfer function of the system. So this is C, this is A, this is B. All right. So we saw earlier that the transfer function of the system is C Si minus A inverse B plus D. D here is 0 because there is no input term in the output equation. So we just have to find out this transfer function. All right. So first let us find out Si minus A inverse. Do you guys want to try this out? Let's take maybe 2-3 minutes. S plus 29, is it? Okay, anyone else has any answers or we can start solving? Okay, let's start solving and we'll see what answer we get. Plus 29 by S plus 1. Yeah, it might be the case. I'll just start. So first let us find out Si minus A inverse because that is probably going to be the hardest part in this thing. Here we have S minus 1, 25, S plus 4 inverse. So this we have S square plus 4S plus 25 into uh, S plus 4 S 1 minus 25, right? Yeah. So how do we find out the, so can anyone help me find this solution out? So, okay, yeah. The good thing is we don't need to find out any Laplace inverse here. We just then need to multiply C and B with this thing. So C Si minus A inverse B. D is 0 here, so this is all we need to find out. This is 1 minus 1 C into S plus 4 1 minus 25 S into 1 0. So it's a good thing that we have a 0 here. So first we can just multiply these two and this term will also be there, this term into 1 by something. Okay, so first we'll multiply these two n matrices, so now we'll have 1 by something into, okay, I'll take some more space. So now I have 1 by s square plus 4s plus 25 into 1 minus 1 into s plus 4 minus 25. Okay, then we multiply both of these. So we get s plus 4 plus 25. So that is s plus 29 by s square plus 4s plus 25. So is that right? So your numerator seems to be correct, but perhaps there was a mistake while finding the denominator. So this is the transfer function. Then again, let us just verify it using MATLAB. Okay. So is this visible? Yeah. Yeah. So we have this A matrix 0, 1, minus 25, minus 4, B matrix 1, 0, C matrix 1, minus 1, and D is 0. Okay, so I want to find out, I want to take this state space representation to a transfer function representation. All right. So I'll just run this. Then what I get is the numerator is s plus 29 and the denominator is s square plus 4s plus 25. So this verifies our solution. All right. And so is there any doubts? Are there any doubts? Okay, I'll stop sharing my MATLAB screen. Yeah. So we had obtained this solution, which was verified again by MATLAB. Then we move on to the next question. So remember to stop me anytime if you have any doubts. Then, so what we have here is, which of the following statements is or are true? If g of s is realizable, then g of s is an improper matrix. So before we go into the options, I'll just define few things. So a proper matrix is a transfer function matrix g of s which has proper elements. And what is a proper element? It is just a transfer function whose where the order of numerator is less than order of denominator. Okay. So why is this a proper matrix? And the thing is, you can have, let's say, 5 by s plus 1. You can have a transfer function like this. But okay, let's say you have a transfer function s. So what is the Laplace inverse of s? Can anyone tell me? So the thing is, when you take functions like delta of t, u of t, or any real physical signal, it is usually so when you find the Laplace function of any such signal which is realizable in some sense, then you would usually have something like the order of the denominator would be greater than the order of the numerator. So this kind of becomes does not satisfy the real kind of signals like causal or things like that. So if G of S is a proper matrix, only then is the system realizable. All right. So if in every other case GS is realizable, then also it has to be a proper matrix. It cannot be an improper matrix. And if it is a proper matrix, it is always realizable, which is this option. And if it is an improper matrix, then it is not realizable. So the only correct option is this. Okay. So if this is clear, then we can move forward. Now we come to the final question of the session. So we have a linear time varying homogeneous system. So up till this point, we only had LTI systems. So A and B were very nice constant matrices. But here we have a time varying system. It is an autonomous system, so no control input. So the question is for initial values of this, find a valid fundamental matrix for the system. Okay. So first, let us understand a fundamental matrix. So psi of t, a fundamental matrix psi of t till psi n of t, these are the columns. This is a fundamental matrix if, so an n cross n matrix psi of t is said to be fundamental, is said to be a fundamental matrix for some a x dot of t, a of is equal to a of t x of t, if the n columns of psi, these n columns are linearly independent. Okay, so these solutions, these functions of time, they are linearly independent. Then this is a fundamental matrix for the system. Okay, so if we have two linearly independent initial conditions, then the solution of these two initial conditions will give us two linearly independent solutions. Okay. And for this second order system, those two solutions will give us a valid fundamental matrix. Okay. So first, let us write down we have this. Okay. 0, 2t, 0, 0, x. That means x1 dot is equal to 2t x2 while x2 dot is 0. So this implies x2 of t is equal to x2 naught. So x2 is a constant at its initial condition. So this would imply x1 of t, this would be just integrating it. We'll have t square. So we'll have x1 naught plus t square x2 naught. Okay. So because if you integrate this, an indefinite integration would give us t square x2 naught, given that x2 is a constant x2 naught, and plus some constant, the, okay, I'll just do this. X2 is constant, so we only have this t square plus some constant, and since x1 0 is x1 naught, we'll have x1 of t is equal to x1 0 plus x2 0 t square. So now look at this. X of t can be written in terms of x of 0 by this matrix. Okay, so if you look at this, this tells me x1 of t, x2 of t is equal to 1 t square 0 1 x1 naught x2 naught. Now this you can verify. So x1 of t is 1 t square into this. So we have x1 naught plus t square x2 naught, which is the case. And x2 of t is 0 1 into this, which is just x2 naught. So x2 of t is x2 naught, which is also true. So now to find the fundamental matrix, we need to find the solutions of these two. Okay. So the solutions of these two, these are the initial conditions. So I know this, I want to find the solution. So I have, so for initial condition 1, 2, I'll multiply it with this matrix. That will give me the solution 1 plus 2 t square and 2. Okay. And for this, I'll have the solution 1 minus 2 t square and minus 1. So these are psi 1 of t and psi 2 of t. So that means psi of t is the matrix 1 plus 2 t square 2 1 minus 2 t square minus 1. Okay, so this is a fundamental matrix for the given LTV system. Okay, so is it clear up to this point? So you understand what a fundamental matrix is, right? You have, let's say you have a set of initial linearly independent initial conditions. Then the corresponding solutions would give you a set of linearly independent as solutions to the like x dot equal to ax, that equation. So that forms the fundamental matrix for this system, this particular system. So is it clear? Okay. Okay. So if it is clear, we will solve only that many questions for today. But if anyone has any other doubt relating to some concept in the course videos or something like that, then you can stay back to ask those, or else you may leave.